Okay, I'm going to go over number 3 with water, the drawing the Lewis structure of water. So if you remember, when we did Lewis structures, there's a series of steps that you go through in order to determine what your dot structure is going to look like. So step number 1 is to count up your number of valence electrons. So we have to look at hydrogen and oxygen. We have 2 hydrogens. Each hydrogen has 1 valence electron. Oxygen has 6 valence electrons. That gives us a total of 8 electrons. So that's how many we have to work with. In the drawing of Lewis structure, the next step is to put the least electronegative atom in the middle. In this case, we only have 2 elements. We have hydrogen and oxygen, and hydrogen never goes in the middle. So you need to remember that. Hydrogen never goes in the middle. So we're going to put oxygen in the middle. And then we're going to bond our outer atoms. So we have 2 hydrogens. Okay. Now, remember that you need to keep track of your number of electrons. So we have 2 hydrogens. We made 2 bonds. That's 2 electrons each. So that's 4. So that leaves us with 4 electrons. Next step was to make sure that your outer atoms have the correct number of electrons, which in this case they do because hydrogen only wants 2 electrons, and that is it. No more than 2. So these 4 are going to go on that oxygen. Oh my gosh. Sorry, my cat keeps jumping on my lap. Just okay. And then that uses up our 4 electrons, and now we have none left over. All right, so there is our Lewis structure. We're check oxygen 2, 4, 6, 8. Oxygen has 8 electrons around it. It is good to go. All right, next question is the electron geometry and molecular geometry. Okay, so remember the electron geometry has to do with how many pairs of electrons are around the central atom, and it does not reference what are bonding and non-bonding, are lone pairs. So remember, these guys are lone pairs, the ones that are not bonded to anything. So oxygen has 1, 2, 3, 4 electron pairs around it, which makes it tetrahedral. And then 2 of those pairs are lone pairs. So that means its molecular geometry is going to be bent. So if you remember that chart I gave you, and I'll try to post that on Canvas, it gives you a bent structure when you have those 2 lone pairs. Next question is bond angles. So that was written on that sheet as well. For a tetrahedral structure, our bond angles are actually going to be 109.5 degrees. Next question has to do with polar or non-polar. Now, with polar or non-polar, what you're going to be looking at is your difference in electronegativity values. Remember, triangle means change in, okay, or difference. So our change in electronegativity values. So for that one, you do need your reference sheet. So if you look at your reference sheet, there's a chart down here at the bottom that has electronegativity values for all the atoms. So you need to look at what the electronegativity values are. So for oxygen, it's 3.5, and for hydrogen, it's 2.1. So these guys have an electronegativity difference of 1.4. And that means it is going to be polar. Or sorry, the bonds are going to be polar. So I'm going to have a negative charge on my oxygen and positive charges on my hydrogens. Now, because this is not a symmetrical molecule, because it is bent, that means that overall this molecule will be polar. Now, if I had 4 hydrogens around here and it wasn't charged, which it would be, if I had 4 oxygens around here and it was equally spaced out, even if those bonds are polar, that total molecule is not going to be polar. Okay, so then it would be non-polar, but this one is actually polar. And then the next question is asking about, it says redraw shape and show net dipole if polar. So this is polar. So we're going to redraw our shape. So I'm going to redraw it so that the electrons are on one side and the hydrogens are on the other. I know from my electronegativity differences, these are going to be my positive, my partial positive. Remember, this is a delta, lowercase delta. And then my negative is going to be up here. So I have these dipoles that are pointing towards the oxygen. So those are my dipoles just for the bonds. And then the net dipole points towards that oxygen. So that would be your net dipole. You put a little hashtag at the bottom, or a little hash at the bottom, because it kind of shows you which is the positive and which is the negative. You always point towards the more electronegative, and then the other side is the positive. And then the last one, types of intermolecular forces, it says circle all that apply. Remember that everything has London dispersion. So we have London forces on this one. And then we just have to determine, is it dipole-dipole or hydrogen bonding? So for hydrogen bonding, remember that you have to have hydrogen bonded to one of these three, N, O, or F. Okay, only those three. Well, in this case, we have hydrogen bonded to oxygen, so that means it is also going to have H bonds.